So, good morning, everybody. Welcome to the latest edition of the Pangolin Seminar. Today, Carvajales from the Ruprecht-Karls-Universität Heidelberg is going to speak to us about the growth of quadratic forms under Anosov subgroups. So over to you, Leon. I hope I pronounced your name correctly.
Yes, perfectly. Okay, so thank you very much for the invitation. I'm very happy to speak here. So I am sharing my screen now. Can you see it well?
It's great. It's great.
Okay. So I will speak about this this work, which is called the growth of quadratic forms under Anosov subgroups. So this work is concerned with what is called the counting problems. So I will start with a brief introduction to the classical orbital counting problem. Okay, so in the very classical setting, we consider the following: consider a Cartan-Hadamard manifold. By this I mean a simply connected, complete Riemannian manifold with non-positive curvature, and I take a discrete group of isometries of this manifold. I take a base point in this manifold, and I take the orbit of this base point by my my discrete group of isometries. So I get a discrete subset of my manifold. And now for each positive t, I can consider the ball of radius t centered at this base point. And the orbital counting problem, that what wants to understand is the asymptotic behavior of the function that counts how many elements of my group move this base point to a point in the ball of radius t. Okay, so what do I mean by understanding asymptotic behavior? I mean to find a more or less explicit function such that this quotient goes to 1 as t goes to infinity. Okay, so I want to understand if this function is a polynomial, if it is an exponential, I mean, to find more or less explicit function that satisfies this. Now, this is a very classical problem. I mean, I will only mention a few instances where this problem has been studied. So the first one that studied this problem was Gauss, who treated the case of the integer lattice in RD. And in that case, you can show by a simple geometric argument that, in fact, your function is asymptotically t to the power of d. Okay, so how do you do that? The idea is purely geometric. Okay, so you take a big ball of radius t, you cover your ball by fundamental domains of the action of your group. Of course, these domains, the fundamental domains, do not fit perfectly in the ball. There is an error which occurs around the boundary of the ball. But the point is that the volume of the boundary is of order strictly smaller than the volume of the ball. Okay, and so this allows you to actually conclude that the counting function is asymptotically a constant times t to the power of d, which is roughly the volume of the ball. Now, if you want to do the same, play the same game, but for, let's say, a co-compact lattice in hyperbolic space, you get nothing. Essentially because the volume of the boundary of the ball is equivalent to the volume of the ball. Okay, so maybe you get an exponential growth, but you cannot find by this argument a precise asymptotic for the counting function. And of course, we know the answer for this problem in this setting. But what I want to emphasize here is that the proofs that we know always involve techniques which are not purely geometric. So many people worked in this negatively curved setting, but a central contribution to this theory is due to Margulis in his PhD thesis. He studied this problem for the case of the universal cover of a closed negatively curved manifold, and for the action of the fundamental group in it. Okay, and in this case, Margulis shows that the counting function is asymptotically a purely exponential function. Okay, in fact, the exponential rate. So the key idea of Margulis is to use dynamics. Okay, so he studies the ergodic theory of the geodesic flow of the manifold. And this exponential rate that he gets, it is in fact the topological entropy of the flow. And since the contribution of Margulis, it is quite standard in order to study these counting problems to actually try to find some suitable flow and to try to study the ergodic theory of this flow to try to understand your geometric problem. Okay. Now, a fairly general result in the negatively curved setting has been obtained by Roblan some years ago. And I want to mention a third example. Okay, so the example that I want to mention is what is called a higher rank symmetric space of non-compact type. Okay, I won't define this right now, but what I want you to keep in mind is that this is a symmetric. This is a Cartan-Hadamard manifold that contains both totally geodesic copies of hyperbolic planes, but also totally geodesic copies of Euclidean spaces. So it is in some sense a mixture between the first two examples. And in that case, there are some relevant work. So for instance, you have the work of these people, Duke, Rudnick, Sarnak, and Eskin McMullen, who treated the case of a lattice in G. Okay? And in this case, the authors show that the counting function is asymptotically a polynomial times an exponential. So you really see the mixture between the first two examples here. Okay? And there is also some work that I want to mention here, which is work of Kahn, Tyrion, and Sambarino, who treat the case of what is called a delta Anosov subgroup, and I will define this notion later. And in this case, the authors show a purely exponential asymptotic. Okay, so I wanted to mention these three examples just to summarize what kind of things can happen in this problem. Okay. Now, in this talk, what I want to discuss is what happens if we replace the base point by a totally geodesic submanifold of X. Instead of taking a base point in my Cartan-Hadamard manifold, I want to consider a totally geodesic submanifold. Okay, and I won't discuss this problem in general. I will discuss it in a very concrete setting. So I will define these spaces of quadratic forms. Okay, so for positive integers P and Q, I will consider the space of all quadratic forms of signature PQ on RD, okay, where D is the sum of these two integers, okay? Now, PSLDR acts on this space by push forward, okay? And in fact, this action is transitive. And the stabilizer of a point is what is called this special orthogonal group, okay? So it is the group of linear isometries of a quadratic form of signature PQ. Since P and Q are positive, this group is non-compact. Okay, so this is a space that I want to keep in mind for this talk, and the other space that I want to keep in mind is what is called the Riemannian symmetric space of SLDR. So it is in some sense a special case of the former space. It is the space of all inner products on RD. Okay, so it is a space of all quadratic forms which are positive definite on RD. And because of the same argument, we have that it is in fact a homogeneous space of PSLDR, but this time the point stabilizers are always isomorphic to PSOD. So in particular, they are compact. This implies, in fact, that this space carries a PSLDR invariant Riemannian metric. And it is a deep fact that any PSLDR invariant Riemannian metric on this space turns this space into a Cartan-Hadamard manifold. So it is a ball of some dimension. But what I want to emphasize here is that it contains flats in general. Okay, so the curvature is not strictly negative. Okay, so there exist in this space totally geodesic copies of Euclidean spaces. And so a fact that I want to mention here is that whenever I pick a base point in my space of quadratic forms of signature PQ, I can get a totally geodesic submanifold of this space of inner products, okay, which is in fact isometric to the Riemannian symmetric space of the stabilizer of the base point, okay? So the stabilizer of the point O is isomorphic to PSO PQ, and to each base point O, I can associate a totally geodesic submanifold of my Riemannian symmetric space, which is isometric to the Riemannian symmetric space of the stabilizer. Okay, so here's the picture in mind. It's maybe a bit abstract. To each base point in my space of quadratic forms of signature PQ, I associate some totally geodesic submanifold of my Riemannian symmetric space. And maybe just to have a concrete example in mind for those who are not very used to this type of constructions. So if we consider the case of SL2R, okay, and we consider P and Q to be equal to 1, So a quadratic form of signature 1, 1 gives in fact that there is a way of associating to such quadratic form a geodesic in H2. Okay, so this submanifold SO will be a geodesic in H2 in that case. But of course, the case that I want to treat is a higher rank case. Okay, so maybe a concrete but a bit more interesting example for our purposes should be that I consider the case of SL3R. I take P to be equal to 2 and Q to be equal to 1. And this submanifold SO is a totally geodesic copy of hyperbolic plane inside the Riemannian symmetric space of SL3R. Okay?
Can I ask a small question, just to fix ideas? So you have a function which sends a QPQ into the space of totally geodesic submanifolds of QD, right? Is this function injective?
Is this function injective? That is a good question. Okay, never said. I think it is, yes, but we have to check it. Yes. Okay. I would say it is, but I would have to check it carefully.
Okay.
So maybe, yeah, I guess so. Maybe so. So what is a concrete way of realizing this this submanifold? Okay, so this submanifold will be a subset of inner products in RD, and an inner product will belong to the submanifold SO if and only if you can find an orthonormal basis on RD for this inner product such that it is also orthonormal for the quadratic form O. So I think that with this characterization you can show that the function is injective, if I'm not mistaken. I think that yeah, I think that probably this gives you your answer. Okay. Okay, we have to check this carefully.
Thanks.
Okay, so now what I want to do is the following. I want to fix a discrete subgroup of PSLDR, and I want to look at the orbit of this submanifold. Okay, so I take my submanifold SO and I move it by an element of PSLDR, so I get another totally geodesic submanifold. And I want to compute the distance between these two submanifolds. Okay, so by this I mean I take the infimum, the minimal possible distances between points in SO and points in G of SO. Okay, and the orbital counting problem that I want to study is to try to understand how many elements of my discrete group move this submanifold into a submanifold which is a distance at most t from the original one. Okay, so instead of taking a base point, I take a submanifold and I look at the orbit of this submanifold. And this is a problem that has been studied in a negatively curved setting. So in particular, there is work of Arconen and Polan who studied this problem for the universal cover of a negatively curved manifold. But what I want to emphasize here is that the space that we are looking contains flats. So this makes the orbital counting problem more involved in some sense. And I also studied this problem for this pair PSO-PQ and PSO-PQ minus 1. Okay, so here the underlying pair that we are looking is PSL-DR and the PSO-PQ. But in previous work I did this, I studied this problem for PSO-PQ and PSO-PQ minus 1. Okay, so I will state the first results towards the understanding of this counting problem. So I will consider the delta Anosov representation. This is a representation from a word hyperbolic group into PSLDR that comes equipped with a limit map. So it is a continuous map from the Gromov boundary of the group into the space of full flags of RD. Okay, so the space of full flags of RD is the space of sequences of nested subspaces of RD of all possible dimensions. Okay, So one requires a representation is delta Anosov if it admits such a map, which is continuous, and a central property that this map has to satisfy is that it must be transverse. This means that whenever I take two different points in the boundary, x and y, when I look at the line associated to y, it must be transverse to the hyperplane of x. When I look at the two-dimensional subspace of y, it must be transverse to the d minus two-dimensional subspace of x, and so on. Okay. This is a central property that one requires, and there is also a uniform contraction dilation property that one asks, which is that some flow admits a hyperbolic splitting, which I won't state here precisely. But let me say that this notion has been introduced by Labourie and Guichard-Binard. Okay, so Labourie introduced this notion for when gamma is the fundamental group of a closed negatively curved manifold, and Guichard-Binard extended this notion toward hyperbolic groups. And this notion provides a stable class of quasi-isometric embeddings of hyperbolic groups into higher rank semi-simple groups, which it is fairly accepted nowadays that this is in fact an analog of convex compact representations. Okay, so if your group, if your target group has a rank 1, then a representation is Anosov if and only if it is convex compact. Okay, so it is a generalization of this notion. Okay, and some examples. So maybe the easiest example is what is called a Schottky subgroup of PSLDR. Okay, so in the same way that you can play a ping pong in the boundary of hyperbolic space to get a free discrete subgroup of isometries of hyperbolic space, you can do the same. You can play ping pong in the space of flags. Okay, and you can get a discrete subgroup of PSLDR, which is in fact delta Anosov. But in some sense, a more general, a more interesting example is what is called a Hitchin representation. So you consider the fundamental group of a closed surface of a genus at least 2. You embed this into PSL2R in a faithful and discrete way. Okay, so you embed this injectively with discrete image in PSL2R, and then you compose with an irreducible representation from PSL2R into PSLDR. And then you take any deformation of this representation. So Hitchin showed that in fact that the space of all these deformations is a ball of some dimension. Okay, so in some sense it generalizes the Schmirer space. Labourie showed that in fact all these deformations are delta Anosov, and in particular they are faithful and discrete. Okay, and so maybe a good example to have in mind is still the case d equal to 3, where in fact Choi and Goldman showed that Hitchin representations in this setting parameterize the space of convex real projective structures on the surface. Okay, so every Hitchin representation in PSL3R preserves some convex set on projective space and acts properly discontinuously and co-compactly in there. So it induces real projective structure on the surface. And in fact, this Hitchin representation space in that case is precisely the space of projective structures on the surface. Okay, so this is maybe an example to have in mind. And another example of a delta Anosov representation, which is different in flavor, is so you play the same game and you embed the fundamental group of your surface into PSL2R, and then you compose with a reducible representation, let's say into PSL3. And then you perform small deformations of this. These are always delta Anosov, okay? But the main difference is that, or one main difference is that large deformations of this representation may lose this property, okay? Okay, so the first results that we want to discuss are the following. So I take a delta Anosov representation and I define this set omega rho. This will be a subset of my space of quadratic forms of signature PQ. So a point will belong to the set if and only if, when I restrict my point, which is a quadratic form, to each of the subspaces of this flat curve, is non-degenerate. So okay. So this is an invariant subset of the space of quadratic forms. So to keep things concrete, when P and Q are equal to 1, and I'm working in SL2R, I said that a quadratic form of signature 1, 1 induces some geodesic in H2. And we can interpret this set omega rho as the set of points such that the associated geodesic is disjoint from the limit set. Okay, so the two final points in the boundary of the geodesic is disjoint from the limit set. But still, I mean, I am focusing in a higher rank example. So when P is equal to 2 and Q is equal to 1, I said that, for instance, a Hitchin representation preserves a convex set in projective space. And whenever I take a quadratic form of signature 2, 1, such that the isotropic cone of this quadratic form is disjoint from the boundary of this convex set, this is a quadratic form that belongs to this set omega. Okay? So all this to mention that, I mean, there are examples of representations in which this set is non-empty, and one can consider the action of your group in this set. And in fact, in joint work with Florian Stecker, which is still in progress, we can show that this set is a domain of discontinuity for the action. Okay, so it is a subset of the space of quadratic forms, is invariant, and the action of gamma on this set is properly discontinuous. Questions? Okay, so we have this space, okay? So all quadratic forms, which in restriction to all the subspaces of the limit set is non-degenerate. And something that one can show more or less easily from what we know about Anosov representations is that...
Excuse me, Jeremy Tudis has a question. He wants to know if the action is co-compact as well.
I wouldn't expect that. I don't know, but I don't expect that. I mean, so in some sense, this set omega rho should be thought as a generalization of. Okay, so I will say some words here. So for instance, when you take a convex or compact representation into SOPQ, okay, this set omega rho would be the maximal invariant convex domain. So the action in that case is co-compact in some subset of this guy, okay? And this omega rho would mimics the large set, okay? I don't know about co-compactness. I mean, we are still trying to understand this construction of a domain of discontinuity, and then maybe try to see if we can, inside this domain of discontinuity, try to define maybe some kind of convex hole or something like this, in which the action would be co-compact, but I don't know for the moment. Okay, so something which it is not super hard to show from what we know about the Anosov representations is the following. So assume that the representation is Zariski dense. This is a technical hypothesis. In this case, we can find a positive constant delta with the property that whenever we take a base point in this set omega rho, then the counting function that we want to understand is bounded between two purely exponential functions of this rate delta rho. Okay, so of course I would like to prove an asymptotic of this function, but for the moment, I mean, this is something that one can prove, which is not extremely hard to prove from what we know about Anosov representations. And in fact, very roughly, the idea goes as follows. So the idea is the following. So you take any point in your submanifold SO, and in fact, you can show that the distance from SO to gamma of SO, when you compare this distance to the distance of from tau to gamma of tau, this is bounded in gamma. Okay, and once you obtain this uniform bound, we know that this the counting function associated to the choice of a base point and its orbit is purely exponential. This is the result of San Marino that I quoted at the beginning. So this uniform bound gives you directly this this lower and upper bound for the counting function. Okay. Of course, I would like to understand an asymptotic of this problem, but this is something which is not very hard to prove from what we know about Anosov representations. And then what I want to do now is to describe some results in the direction of trying to prove that this function is actually asymptotically pure exponential. Okay. So what I want to describe now is a precise asymptotic result for a counting function which is related to this one. Okay, it's not precisely this one, but it is related to this one. So the result, to actually state it, what I want to discuss is a way of expressing the distance from the submanifold SO to its image in a literatic way. Okay, and in fact, what I will discuss is a generalization of what is called the Cartan decomposition of PSLDR. So I will briefly recall what this is. So in order to do that, I want to recall that a flat, or I will call a flat of the Riemannian symmetric space, a totally Chelsea copy of R to the power of D minus 1 inside this space. This is what I call a flat. And in fact, the space of flats is in one-to-one correspondence with the space of projected bases on RD. Okay, so a basis of lines is just a set of D lines in RD that span RD. And the choice of such a basis is the same as the choice of a flat, or is the same as the choice of what is called a Cartan subspace. So if I am given my set of D lines that span RD, the flat is just the set of all inner products which make this set orthogonal. Okay, and the Cartan subspace is the set of all traceless matrices which are diagonal in this basis. Okay. There is always some kind of a dictionary between geometric objects and linear algebra and Lie theory, and I want to play this game. Okay. So what is the classical Cartan decomposition? I fix a base point. Remember that this is an inner product. And I can write PSLDR in this KAK decomposition. So K is the stabilizer of my point. So there is a maximal compact subgroup in PSLDR. A is a flat that passes through the base point, which means, I can say it in another way, is the basis of lines determined by this flat is orthogonal with respect to the base point. And A plus is the choice of a Weil chamber. Okay, so what is a Weil chamber? I mean, there are many ways of defining it. I will define it in a geometric way. So flats in our space SL, let's say in SL3R, are divided in 6 sectors. And each one of these sectors is what is called a Weil chamber. And a ray is contained in the interior of a Weil chamber if and only if the flat A is the unique flat of the symmetric space that contains this ray. So these rays here that I'm trying to point with my stuff here, which I don't know how to say in English, these rays here belong to the flat A, but belong to infinitely many flats of the Riemannian symmetric space. Okay, so the interior of the Weil chamber is precisely a set of rays that belong only to one flat of the symmetric space. Okay, so we have this Cartan decomposition, and in fact, there is a geometric way of saying, of expressing the part of the content of this result, which is to say that for every element in PSLDR, I can find a flat that passes through the base point tau and through its image by G. Okay, this is another way of expressing at least part of the content of this Cartan decomposition. And in fact, since the coordinate, the A plus coordinate is uniquely determined, one can define a projection.
Excuse me. Yeah. Just a silly question. So just to get this right, the Cartan decomposition then states that every element of PSLD can be written uniquely as a product of KAL, where K and L are elements of KT, and A is an element of this exponential of the Weil chamber. Is that correct?
Yeah, so the uniqueness is I mean, there is the K and the L may not be unique.
Oh, right. Oh, right. I see.
But the A
Right.
plus coordinates, the A plus coordinate, it is unique.
I understand.
Okay. And so I can actually take this A plus coordinate. This is well defined. And there is a fact that the norm of this vector coincides in fact with the image from tau to g of tau. Okay. So this is a one way of giving an interpretation of this Cartan decomposition. And in fact, what I want to do is to play the same.
So excuse me. Yep. So this is a sort of projection then onto the Weyl chamber.
Yes.
Right. Yes. Okay. So is the restriction of the exponential to the Weyl chamber a bijection onto its image?
Yes. Yes. Yes.
Right. I see. So really, you really are projecting onto the Weyl chamber.
Yes.
Okay. Great.
And in fact, there is a way of lifting the Riemannian metric of the symmetric space into a norm in this Cartan subspace. And the norm of the vector of this projection coincides with the distance from tau to g of tau. Okay, this is one way of interpreting geometrically the Cartan decomposition. Okay, and so what I want to do now is to play the same game. Instead of working with a base point and its image, I want to work with my submanifold and its image. Okay, so I want to play the same game, but for this quantity here. And so I define the following set. The set, so I take a base point, which in this case is a quadratic form of signature PQ, and I define the set of elements in PSLDR for which I can find a flat which is orthogonal both to SO and to G of SO. Okay? So this is a subset of PSLDR. It will not coincide with PSLDR in general. So for instance, you can think in the simpler case, which is PSL2, and this submanifold SO was a geodesic. And it is not true that for every element of PSL2, I will be able to find a flat, which will be a geodesic, which is orthogonal both to the original geodesic and to its image. For instance, if my element moved the geodesic into a geodesic that intersects this original geodesic, there will not be a common orthogonal. But I want to focus on elements that for which I can actually do that. Okay. So I will define the set of these elements. And in fact, something that we can show is that this set admits somehow a Cartan decomposition. Okay. So it can be written like this. It is h times w times exponential of b plus times h. So h is the stabilizer of my quadratic form. So it is isomorphic to PSO-PQ. B is a flat, but it is a flat that I fixed at the beginning, which is orthogonal to my submanifold. Okay, so the property that I require to be is that it is orthogonal to SO. W is the bigroup of this flat. Okay, so recall that my flat in this case is determined by the choice of D lines in RD that span RD. The bigroup is just the group of permutations of these lines. And the B plus is a Weyl chamber, but it is a generalized Weyl chamber. Okay, so to describe what this Weyl chamber is, I will work in D for D equal to 3, P equal to 2, and Q equal to 1. Recall that in this case, my flat was divided in 6 sectors, but in fact, this Weyl chamber B plus is just a half space in there. And the rays in the interior of this Weyl chamber are characterized by the property that they only belong to one flat of the Riemannian symmetric space, which is orthogonal to SO. Okay, so you see here, this ray here, it belongs to infinitely many flats of the Riemannian symmetric space, but only one of these flats is orthogonal to SO. Okay, and this flat is B. So in this sense, in the new setting, this ray is a regular ray. Okay. I don't know if this was clear enough, but other questions?
I actually have a question. So what's the dimension of B in general? Is it the codimension of the rank of SOPQ inside SLN?
No, in fact, in
SLD?
this case, it is always maximal. It is a Cartan subspace of SLDR. So this means
B has always the same dimension as A. It's just a union of Weil chamber, right?
in this case, yes, there are symmetric spaces for which it's not. But in this case, it is a Cartan subspace, so it coincides with A.
Yeah, but is it? I mean, for D equals 3, P equal 2, Q equal 1, that's the same. But in general,
For
you say
any P and for any Q, it is yes. What I'm saying is not in general is that for any symmetric space, so for any pair GH, it is not true that the flat B will be a Cartan subspace. But for this family of symmetric spaces, so PSL-DR and PSO-PQ, it is always a Cartan subspace.
Okay, I see. Thank you.
Okay, so we have this generalized by chamber, okay, which can be defined like this, okay? So rays in this Weil chamber are regular if they only belong to one flat, which is orthogonal to the submanifold SO, okay? So we have this generalized Cartan decomposition, and we can take the projection, okay? So we show that the B plus coordinate is uniquely determined, and in fact, the same result, almost by construction, it holds that the norm of this projection is the distance that I want to compute. Okay. This follows almost from the construction. I mean, it is constructed in such a way that this holds. And something that we can also show is that whenever, if I am given an Anosov representation, and if I take a point in this set omega rho, then large elements of my group belong to this set BO. So in particular, I can compute, I can take its Cartan projection, its generalized Cartan projection. So the result that I want, or the problem that I want to understand now becomes this lit-theoretic problem, okay? So I want to understand how many elements of my group gamma have this generalized Cartan projection with the norm less than or equal to T. Okay, so this is just a lit-theoretic traduction of the problem that I was stating at the beginning. Okay. Okay, so I insist that this is the problem that I want to understand, and I still cannot give a full answer for this problem, but we can give some partial answers. So assume that the representation is Zariski dense, and that I take a base point in this set. And I will assume also a technical hypothesis, which is that when I restrict my quadratic form to all the subspaces of the limit set, the signature that I get is constant along X, okay? So all the lines of the limit set have the same sign for the quadratic form O. All the two-dimensional subspaces of the limit set have the same signature for the quadratic form, and so on, okay? So I have this technical hypothesis, and under these conditions, whenever I take a functional in the interior of the limit cone, so the limit cone is this object here that was introduced by Benoit, okay? So it is the set of, roughly speaking, the set of all limits of all Cartan projections of gamma. This is an object that encodes many asymptotic properties of gamma, and in fact, Benoit showed that this is a cone, closed cone, which is convex and has non-empty interior. Whenever I take a functional in this cone, so I can consider the counting function that instead of looking at the Euclidean norm of this Cartan projection, I can evaluate my Cartan projection in this function. Okay, so I get a number. And what I want to do is to count how many elements of my group have this number less than or equal to T. And for this counting function, we can prove a precise asymptotic. Okay. So this is the problem that I would like to understand. I would like to understand what happens with the growth of the Euclidean norm of this generalized Cartan projection. But for the moment, we can show an asymptotic whenever I take a function in my Cartan subspace and I compute the norm in some sense with respect to this function. Okay. Okay, so I will briefly discuss some lines about the proof of this theorem. The first thing that I want to discuss is how to find a concrete way of working with this generalized Cartan projection. Okay, so I define this generalized Cartan projection by defining some subset of G and decomposing this subset in some way and taking some coordinate in this decomposition. But there is a concrete way of working with this generalized Cartan projection, which is the following. You use the symmetric structure of the pair PSLDR HO. Recall that HO was the stabilizer of my quadratic form. Okay, so it is isomorphic to PSO-PQ. What do I mean by the symmetric structure? Well, the group HO can be described as the fixed point set of some involution in PSLDR. So in the same way as, so when you take, you can describe a PSOD, okay, so the definite orthogonal group as the set of matrices which are antisymmetric. Well, you can do the same, but so you take the adjoint with respect to your indefinite quadratic form, and your group HO will be the set of, will be the group of antisymmetric elements with respect to this adjoint. Okay, so there is some involution there that for which the fixed point set is the stabilizer. The flat B is orthogonal to SO. This was by choice. This will imply that in fact the action of this involution on B is coincides with the minus the identity. Okay, so it takes every element to its opposite. And so these two items, in fact, allows us to show the following. So suppose that we take an element in this set BO, and suppose moreover that we can write it as H times exponential of its Cartan projection times H tilde for some elements H and H tilde. These two items that I said here imply that when I compute this matrix here, sigma of G inverse is in fact, well, it is given by this, okay? So the fact that sigma fixes all elements of H and acts as minus the identity on B implies that if G has this form here, then when I compute sigma of G inverse, I get this. And now you see that if I multiply G on the right, sorry, in this equality, in fact, the H tilde, the H, sorry, cancel. And what I get is that sigma of G inverse times G is this product here, okay? H tilde inverse times this Cartan projection times H tilde, which means in particular that sigma of G inverse times G is conjugate to this Cartan projection, okay? So in particular, it means that this product, sigma of G inverse times G, is diagonalizable. And moreover, the Cartan projection is determined by the eigenvalues of this product. Okay, so the eigenvalues are the same. So this lambda is a vector that collects all the eigenvalues of this product, sigma of G inverse times G. And so my generalized Cartan projection, I can interpret it just as a set of eigenvalues of some product of two matrices, which is the matrix G and the matrix sigma of G inverse. And what I want to emphasize here is that this gives me a concrete way of working with the generalized Cartan projection. Okay, so I will move into try to explain how to use this to work with this Cartan projection. So now if I am given a delta Anosov representation, then the problem that I want to understand, I can restate it like this, okay? So I want to understand how the eigenvalues of this product, sigma of rho of gamma inverse times rho of gamma, grows, okay? And okay, so to try to understand this, the structure goes more or less as follows. So a central property of elements in the image of an Anosov representation is that they are proximal. Okay, so when I take any gamma and I look at the rho of gamma, this is a matrix in PSLDR, it acts on the space of foot flags with some kind of north-south dynamics. And in fact, Benoit shows that this is a lemma that Benoit proves in some of his papers, that you can obtain a precise estimate of the eigenvalues of a product of two proximal matrices in terms of the eigenvalues of the matrices. And concretely, in our case, what this gives us is that the eigenvalues of the product of this matrix sigma of rho of gamma inverse times rho of gamma, it can be made arbitrarily close to the eigenvalues of rho of gamma plus some error term, which is called the cross ratio. Okay, so the cross ratio is an object that measures the relative position between the attractors and the repellers of these two matrices that I'm multiplying. Okay, so it generalizes the cross ratio of 4 lines in RP1. Okay, and it is an object that I am not defining, but I want to emphasize that it has a very explicit formula that you can work with. Okay, so I have this result by Benoit that tells me that to pass from the eigenvalues of this product to the eigenvalues of gamma, I have to pay with this quantity, which is the cross ratio. Okay, so the theorem that I want to prove is related to this geometric quantity. Remember that this stuff here is in some sense encoding the distance from SO to gamma of SO. So I will call this quantity a geometric quantity. And Benoit tells me, okay, there is a dynamical quantity that you can take, which is this lambda of rho of gamma, so the eigenvalues of gamma. And I will explain why I call this quantity a dynamical quantity. But what Benoit tells me is that the link between the geometric quantity and the dynamical quantity is given by this cross ratio. Okay, so to go from one to the other, I need to pay with the cross ratio. Okay. So why do I call this quantity phi of lambda of rho of gamma a dynamical quantity? Well, because of the work of Bridgman, Canary, Laurier, San Marino. So these guys prove that, in fact, whenever you are given a linear functional which is positive in the limit cone, and so in the limit cone of an Anosov representation, then you can build a flow associated to this functional and to this representation, which is a flow in a compact space that has the property that the periodic orbits of this flow are in correspondence with the conjugacy classes of elements of the group. And in fact, the period corresponding to such a conjugacy class is given by this number. Okay, so this is why I call this quantity a dynamical quantity. Okay, so it encodes the periods of my flow. And in fact, a central property that BCLS prove is that this flow is a metric Anosov flow. Okay, so because I won't explain what this means, but it implies, thanks to work of Polycott, that one can apply a thermodynamical formalism for this flow. So in particular, we know a lot of the ergodic theory of this flow. Okay, so what do we know in particular? So we have our flow with these periods. We have our Markov coding, so we can apply thermodynamical formalism. So results by Bowen and Parry and Polycott tells that we have this convergence here. So this is a rough formula, but so the objects that appear here are, on the one hand, this H rho phi is just the topological entropy of the flow. It is a positive finite number. The measure of M tilde on the right is the measure that comes from the measure of maximal entropy of the flow. So there is, up to scaling, there is only one measure maximizing entropy, okay? And the measure M tilde comes from this measure. And the deltas here are the Dirac masses at the attractors and repellers of the group acting on its boundary. Okay, so this result can be interpreted like this. So this sum that I'm taking here can be interpreted as just taking the average of the Dirac masses over periodic orbits of my flow. I normalize by the amount of periodic orbits that I have of period less than t. And the result by Bowen tells you that this equidistributes towards some special measure, which is the measure of maximal entropy of the flow. So this is a bit abstract, okay? So, and in fact, it is a purely dynamical result. What do I mean by this? So this flow is not a canonical flow in the sense that its construction is in fact, so what BCLS do is to construct a conjugacy class of flows, okay? So the flow phi t is well defined up to Holder equivalence, okay? So the this is purely dynamical. There is no a priori geometric meaning for this flow. So the challenge is to try to find an explicit representative of this flow, which is geometric in some sense. Okay, so in some sense, try to find an explicit geometric representative of this flow that encodes the geometric information that I want to understand. So far, the information that we obtain by dynamical methods only tell us something about the periodic orbits of the flow. Okay, and this is what I want to do. And so I have these conversions here, and the key names here to understand this method are the names of Margulis, Patterson, Sullivan, and also in this context, Ledrapia and Sambarino, that tells that in fact this measure M tilde, which comes from which is the measure of maximal entropy of the flow, can be written in many ways in an expression like this, okay? So mu, gamma, mu plus, and mu minus are just finite measures on the boundary of gamma that are quasi-invariant under the group, okay? And the bracket here is a continuous function that it is determined by mu minus and mu plus, okay? So in fact, so since these measures mu minus and mu plus are quasi-invariant, when I act on this product with an element of gamma, I get some other equivalent measure, and this bracket is the correction factor that you need to put in order to this measure M tilde to be invariant under gamma. Okay, and so the geometric step is the following. What we want to do is to find explicit measures mu minus and mu plus, such that when I compute this bracket, it encodes the cross ratio. Okay, so more explicitly, I want to find explicit measures mu and mu minus such that when I evaluate my bracket in gamma minus and gamma plus, I precisely obtain the cross ratio given by the estimates, given by Benoit's estimate. Okay? And recall that Benoit's estimate tells me that to go from this dynamical quantity to the geometric quantity, I need to pay with the cross ratio. So now that I have this convergence, which is an abstract dynamical convergence, but that I find these explicit measures for which the bracket is the cross ratio, I can replace in this sum here, I can replace the periodic orbits by the geometric quantity that I want, paying with the cross ratio. Okay, so paying with this factor here, and obtain these conversions here. Okay, where I am summing over my geometric quantity instead. Okay, and once you obtain these conversions, then you just have to evaluate in the total space to get the asymptotic that you want. Okay, so I think that I am finished. Thank you for your attention.
Well, yes, please unmute your speakers and thank the speaker. I'm impressed, Leon, that I'm impressed and surprised that you finished your talk exactly in time. that took me aback rather. Well,
I was scared that it was too long, so I am thinking that maybe I was too fast.
no, it's wonderful. It's wonderful. Are there any questions? So we always have to wait just a little bit for questions. There's always a bit of a delay in Zoom. Well, if there's no other questions, if there's no questions, I have a couple of my own. So in your counting estimate, you have this H5 row, right? So that's in your theorem. You have this H5 row. Now, this H5 row, as far as I can tell, it's the topological entropy of this flow, phi t, isn't it?
Yes.
That's right. But as far as I can tell, you don't have an explicit formula for H5 row in terms of, I don't know, geometric properties of the representation rho. So this H5 row is a mysterious quantity that comes out of this flow phi that's also itself rather mysterious. Would that be right? So the question is, do you have an explicit formula for H5 row in terms of geometric or group theoretic properties of the representation?
Yeah. I think that this is a very good question. So this, in fact, so there is work by Sambarino who shows that, in fact, it is in some sense the critical exponent for the action in the Riemannian symmetric space. Okay, so when you take a base point in your Riemannian symmetric space, you look at its orbit, you consider this counting function, but you only interest yourself in the exponential growth rate. Okay, and so you get the set of all these Cartan projections, and if you evaluate your Cartan projection in your functional phi, and you take this exponential growth rate, this would be like the critical exponent.
I see.
And in fact, this topological entropy coincides with this.
All right. Okay. Okay. I see.
But Graham, it also depends on the phi, no? So
yeah. Yes.
It also depends on the function, so it's not completely purely geometric.
Okay. Okay. So this U minus and U plus, you spoke about explicit constructions of this mu minus and mu plus, didn't you? Which actually make. Now I'm guessing this is the meat of your result. Is it difficult to find mu plus and mu minus, which give you this property that your function is equal to Benoit's cross ratio?
Yeah, I will say a few words. So
please do.
So
I'll just close my microphone whilst you do that.
In the more classical setting, there is these measures called the Patterson-Sullivan measures, which are defined by the Bussmann cocycle, okay, of gamma. It means that so you have to fix a point, and the Bussmann cocycle gives you, for each element of your group and for each element of the boundary, you can compute the Bussmann function based at this point in the boundary from the base point in your space and its image by the element of the group. Okay, so maybe maybe it's a good moment to share my screen in the iPad, maybe. So okay. Okay. So in the very classical setting, what you have is so you have your let's say your H2. You fix a point, call it tau. You have an element gamma of your group. And you have an element in the boundary, let's say of H2. And so you define the following function. It's just the Bussmann function. Okay, so you have your element psi. You consider this horosphere here. You move also your point by your element gamma. You consider this horosphere here. And you compute somehow, compute this distance here with a sign. Okay, and the measure mu is just I mentioned that it was a quasi-invariant measure. So when I act with an element gamma, the function that I obtained, the Radon-Nikodym derivative that I obtained, is given more or less by this. So this is in the classical setting, and the cocycle that I need to consider in my setting is it is defined somehow similarly. So instead of working with a base point, I have a submanifold. I move my submanifold by gamma. And what I do is for my point in the boundary, I project orthogonally here. I get 2 points, this point and this point. And I compute the Bussmann function for these 2 points. So this gives me a function that depends on gamma and on psi. And you can prove that you can build a measure on the boundary such that when you move it by your element gamma and you compute the Radon-Nikodym derivative, it is given by this. And by explicit computations, you can show that, in fact, that the bracket that you obtain, which would be somehow of Gromov product, is precisely the cross ratio. So it is quite explicit in this sense. I don't know if this answers your question.
Okay, I think it did. But just to be absolutely clear then, what you're really interested in is the counting problem in QPQ. And basically what you're saying is that this is equivalent to the counting problem of these totally geodesic submanifolds, these S's inside, I think the space is called QP. Is that right?
Yes. Yes.
So you're interested in the classical counting problem of points in QPQ, and you're shown by what looks a lot like a radon transformation, that it's equivalent to this counting problem of these totally geodesic submanifolds in QP.
Yes, and I still don't know how to, in some sense, I still don't know how to describe this counting problem in the pseudo-Riemannian setting. Itself.
Because you don't have a distance.
Yes, I mean, and I start to describe what is the meaning of this distance between these two submanifolds.
I remember a talk about Olivier. I remember a talk that Olivier Glorieux gave many years ago, where he found a way of addressing this question of distance.
Yes. So the point is that I imagine that Olivier talked about HPQ, which is a very special pseudo-Riemannian symmetric space where we do have like a very concrete geometric picture of this. And in this setting, you can. So in this setting, this distance between these two submanifolds would just correspond to the length of the space-like geodesic connecting the 2 points.
Right, right, which makes sense.
And in fact, this is, I would like to say something similar here, but I cannot.
I understand, I understand. Excellent. Well, everybody, if there are no other questions, then please unmute your speakers, everyone, and let's thank Leon once again for a fascinating talk. Excellent.
Excellent.
Excellent. So people, before, hang on just a second. I need to, oops, hang on, give me a second. I need to spotlight my video. So before I finish the recording, I just want to do a little bit of advertising for the next edition of the Pangolin Seminar. And as everybody knows, the next edition of the Pangolin Seminar will be a very special edition. This will be our beloved pangolin will be celebrating its first birthday on the 20th of April. And so we will have a special talk given by Jean-Marc Schlenker of the Université de Luxembourg. And he will be talking to us about the Weil problem for unbounded convex surfaces in three-dimensional hyperbolic space. So I hope to see everybody there so we can all celebrate the pangolin's first birthday together. So let me stop the recording now.